if you will, on basically talking about algorithms and procedural units, and basically how we talk about making a computer do stuff. Okay, and what does it mean to make a computer do stuff? Okay, so to start, let's just start with the word algorithm. So take a minute and you got some scratch paper or whatever, write down what you think the word algorithm means. Okay, hopefully it's a word you've heard before, maybe you've used it before, maybe you have a technical definition, maybe you don't. What's an algorithm? Okay, so just take a couple minutes and think about that, and then we'll talk about the details. Oh, it does help if I plug power into the computer, otherwise we're going to die halfway through class. That would not be good. And then we'll Google it and see how you guys did. All right, so we got some stuff down. Anybody want to share? Yes. Oh, and where's Cody? I would love to. And this time I won't have to have a mask on in the process. All right, so he'll actually be able to see my full irritation. Yeah, okay. Okay, so let me read that out again and let me type it. So, all right, a set what now? Collect data, check for spelling, grammar. What was the other example? Yeah, create patterns. Okay. Any others? Yeah. Okay, a set of commands that okay. Yeah. A set of remote. Okay. Remote formulas. Okay. Any others? Well, let's see what Hair Google has to say. or hair duck duck go in this case. All right, so we take the word of the bastion of all knowledge of Western civilization, namely Wikipedia, right? So what is it? In mathematics and computer science, okay, right? So this could be context specific, what you mean. An algorithm is a finite sequence of well-defined computer implementable instructions, typically to solve a class of specific problems or to perform a computation. Algorithms are always unambiguous and is used as specifications for performing calculations, data processing, automating reasoning, other tasks. Okay, so I think we actually got pretty good here, right? So there's a couple of highlights here. Obviously, we're in computer science class, right? So the computer implementable part is certainly important. Um, and you know that you can take that how you mean or as you wish, right? Because for example, could we say that baking a cake constitutes implementing an algorithm? Yeah, probably. Okay. Now, I'm not necessarily going to be asking a computer to bake a cake, but I could like make a robot do it potentially. I mean, that would be sort of a good like way to test or demonstrate high level robotics function is to make it do ordinary human tasks. And uh, it's incredibly difficult, as you can imagine, right? Because how, like, if I tell you to bake a cake, what are you going to do? Okay, go find a recipe. Now, where would you find that recipe? I don't know about you guys, but when I'm baking a cake, where am I going to find the recipe? On the side of the box. Okay. I'm not making cakes from scratch. Okay. I'm not that good. Um, but you know, what's this thing on the side of the box going to say? Right? You got the cake mix that's inside, and that's basically got the sugar and flour and all the other stuff, the yeast and whatever else you need. And then what do you typically need to add to it? Some water, maybe some oil, some eggs, right? Huh? Milk, yeah. Basically the stuff that can't be, you know, dry powdered. Um, and you gotta, you know, blend it using or mix it using a hand mixer or a stand mixer or something, which is then great because then you've got the gooey batter all over the little the mixer things. And how many of you guys did your moms let you clean the cake batter off of that? And um, yeah, nobody died of salmonella in the process. Yeah. Okay. Um, well, if you did die of salmonella because of that, you wouldn't be here right now. So this is an example of survivorship bias, right? Anyway, yeah. So you'd go through all that. You'd mix the cake up. You'd put it in the, you know, a greased pan of whatever appropriate size, and you'd pop it in the oven for whatever that says on the box. Okay. Um, and yeah, that's a pretty unambiguous, you know, set of instructions, right? Unless you're a complete moron, you should probably it should probably come out okay. Um, now, as opposed to if I give you a recipe to bake a cake from absolute scratch, okay, might not turn out quite so good. Okay, or all right, maybe a cake isn't the best example because it's a relatively simple thing to cook. But what about if I ask you guys to cook like a souffle, right? Has anybody ever made a souffle? They're incredibly difficult to get to rise properly without collapsing and stuff, right? So, you know, advanced cookery, you know, like Gordon Ramsay level stuff, right, is um, a little bit more exotic, okay, a little bit more complicated. Uh, and Gordon Ramsay, by the way, is one of my favorite chefs because what is Gordon Ramsay famous for other than being a really good chef? Huh? He's ruthless and yeah, you know, he's not afraid to drop an F bomb if needed. So anyway, okay. So yeah, obviously since we're in computer science, right, we want to worry about stuff that's computer implementable, okay? But that doesn't mean that every single example that we're going to look at has to be exactly computer implementable. Okay, so most of you guys are sitting with at least one person, so the kind of couple of you guys that are sort of on your own at a table, kind of group up with somebody else so that you got either two or maybe three people. Okay, and what I want you to do is you'll need two pieces of paper for this. So one of them, just tear it out of your notebook. Okay, uh, and then the other one, just somebody's going to write on it. Okay, so actually tear the other one out of your notebook too, because you're going to end up giving it to somebody. Okay, so with one of the pieces of paper, I want you to fold a paper airplane. With the other piece of paper, I want you to write down the instructions for how to fold that paper airplane. Okay. And now, what does the paper airplane need to look like? I don't care. That's up to you. Okay. And there will be no judgment if your paper airplanes don't fly or if they are terrible looking or whatever. Okay. So there will be no, I will only mock you mercilessly if it's a crappy paper airplane, but there will be no other consequences to this. Okay. And so, yeah, so write down the instructions for what you're going to do, starting with the piece of paper that you've torn off, right? And then give give that a few minutes, and let's see what you guys come up with. While we're doing that, I'm going to see if anybody's on the stream today. Because I feel like we're missing a couple ducks, other than Cody. Cody, I hope you're on Twitch listening, man, because feel free to test out your creations and see how well they fly. Right? We can't have some fun in class, right? That's pretty good. Mhm. Okay, do we have our planes folded and instructions finished? Or getting there? Okay. All right, so we good? We got instructions? Yeah? Okay. Now, hide your paper airplane, put it underneath something, okay? And swap your instructions with one of the other groups. And you can guess what's about to happen. Tear out a third sheet of paper, right? And what do you think you're going to do? Follow their instructions. And if you have to like jumble up your instructions with a bunch of different groups, that's fine. Just be clear where your instructions ended up so that we can compare how good your plane is compared to the OG plane that you're folding. Uh, hmm. Uh-huh. Not a paper airplane. Yeah. Well, and it was a complete disaster, I would take it. Yeah. That's the whole lesson, right? Or part of it anyway. Okay, so once you've finished folding the instructions given by your group that you swapped it with, how are we doing on that? Are we getting kind of close? Almost? You follow the directions that you were given. Okay. Because what we're going to discover, of course, is that well, what do you think is going to happen? Yeah, the airplane that you're going to fold now from their directions is not necessarily going to look anything close to the original. which is going to be interesting, right? And probably also maybe hilarious in the process, right? We can have some good humor from this lesson. Okay, so it looks like we're starting to kind of finish these off. We're getting close. So when you finish it, find the original airplane owner and compare what you folded versus what they had. Okay, and I'd like to see some hilarious examples of the pairs. Okay, so let's see. Let's see a pair. All right, so is this a pair? Okay. All right, I'll come back for those two. Okay, so is this one the original? This one's the original? Okay, so here's the original. Here's the duplicate. Okay, pretty good, I'd say. All right, what about the other two? Which one's the original? This one? Okay, here's the original. Here's the instructions. Okay, also not bad, right? There's probably some hilarious failures though in the group. Uh, okay. Um, I'm going to be charitable and assume that this was the original. And this was the one from the instructions. Okay, which is kind of pathetic, but hey, that's all right. Uh, yeah. Oh, wow. Are you sure you were following the instructions for the airplane and not one of those like stupid? What was the thing that girls in elementary school always made? The like, yes, cootie catchers. Oh, you did? Well, there's nothing wrong with that, Kiani, making cootie catchers. Um, does anybody remember how to make one? Yeah, but you guys know what I'm talking about, right? Yeah, yeah. So, um, okay. So, what was one of the lessons of this? You have to be very clear, okay? And more importantly, though, so this is the one thing where this differs from the fact that we're going to be doing this with computer implementable instructions, right? You guys aren't computers uh, in a most sense of the word, right? You can follow instructions, but not the same way that the slabs of silicon on the desk do. Um, but so what we've learned, right, is that we have to be very precise in our how we encode or write down the instructions. Now, interestingly enough, how did you guys all write down your instructions? You wrote them in English. Okay. Did you have to? Did I ever tell you that you had to write in English? Okay. So what else could you have done? Okay. Yes, you could have written them in Spanish, right? Or any other language. Exactly. You could have drawn pictures instead. Okay. Now, this is a good example because we're at a men's college, which means when you guys were say under 10 years old, what were your favorite toys? Huh? Dinosaurs? Oh, yeah, well, nowadays, right? What about Legos? Was anybody yeah, okay. So, think about the instructions. Okay, have we all built a Lego set in our life from really? Oh, well, that seems like a personal problem. Huh? Yeah. Have you tried to follow the instructions? You've tried? Oh, that's really unfortunate. Well, of course, that's half the point, right? You get Legos, you build them according to the instructions. 2 days later, you tear it apart and build your own stuff. Okay. But you learn something like this is why I think Legos should be like mandatory part of childhood education, right? Because you really do learn something about following instructions that are they're pictorial in that case for the most part, okay? And why does it make sense for the Lego company to produce the instructions as a set of pictures the way that they do? Huh? Okay, depending on the age, kids may not be able to read, okay, or may not be able to read at a sufficient level of complexity for some of the real advanced sets. Yeah. Okay. Yeah. How would you even put it in English? Okay. Or any other language for that matter, huh? Right. It would be complicated. Okay. Exactly. They don't have to write a set of instructions for every language and every market that they're going to be selling these things in, right? Basically, if you go to the Lego websites, where you can nowadays you can just download the instruction booklets, right? Essentially, all of them have like, well, a couple versions, and it's basically only which size of paper do you want to print them on, right? Otherwise, like they don't need a separate set of instructions for the Chinese market versus the Latin American market versus the US market, right? Because it's the same set of pictures, right? Um, and the only sort of written things that are in the manuals are, well, okay, there might be something at the front that kind of like, has Lego copyright information and something along those lines, and the model number and the name of the kit and so on. Okay, but within the instructions themselves, what are the only things that aren't pictures? The numbers for the steps. Okay, so the steps are numbered. Fortunately, basically, most of the world uses the same number system. Um, and on occasion, what do you run into in a Lego set instead of instructions? Huh? I heard it. I thought I heard it. Like a 2x or something, where it'll give you a set of instructions to make something, and then it'll say, oh, make another copy of this. Okay. Um, right. So pictorial representation is certainly possible. Okay. It's interesting that nobody chose to do pictorial representation for the paper airplane experiment here. Now, I didn't tell you guys how to write the instructions, but you all defaulted to putting them in English. Why do you think that is? Yeah. Which is the dude sitting next to you. Okay. Did anybody at least consider doing pictures? Yeah, what were you going to say? I'm sorry. Okay. Because how many of you guys suck at art? Right. Um, yeah. I mean, I'll freely admit it that I'm not very good at drawing stuff, right? Uh, and what I am at least decent at drawing is stuff that's mechanical, Lego-like, or geometric in some way, and that's just because I ended up as a mathematician, right? Big surprise. Um, yeah. Although looking back on it, like I think that was sort of predestined from when I was a little kid that I was going to end up being a mathematician. So it's the best job in the world, I think. Um, okay, so we could have represented this stuff pictorially by drawing like fold lines and the sheet of paper, and we would have to come up with some sort of language for that. What's brilliant, of course, about the Lego, we'll call this a language, if you will, the way the instructions are written, is that do you have to be trained as to how to read them before you can read one? No, if I handed out a bunch of Lego sets and the instructions, even if you'd never seen Legos before in your life, you could probably figure it out. okay? Even if you were, say, a 6-year-old. Okay, now granted, if you're a little kid, you probably have uh, parental assistance or something along those lines, right? But um, you know, think about well, okay, since you're all college students, how many of you guys, when you moved in, you had bought something from like IKEA for your dorm room, like a bookshelf or a sofa or something? What'd you get? A bookshelf. Okay. How'd you put it together? Yes, following the manual. Okay, so what tools did you need? If was it from IKEA or something else? Okay. Yeah, and an Allen wrench because it's from IKEA, right? So of course it's going to involve an Allen wrench. Um, did you get any of the meatballs while you were there at IKEA? No. Oh, okay, you failed then. Um, actually, I've never had the meatballs at IKEA, but yeah. Anyway, um, right. But in some sense, like you know, playing with Legos as a kid uh, turned out to be kind of job training, at least in my case, because you know COVID has kind of thrown a damper on this. But over in the library, I've got a room full of Lego robot stuff. It's yeah, lots of fun. But you know, as I'm sitting there putting gears and wheels and axles and stuff together, and then I'm sending pictures to my dad and be like, "Look, my childhood paid off, right? Now I'm teaching this stuff." So, anyway, okay. So what's sort of the transition point here, right? Obviously, we're not going to be teaching computers to fold paper airplanes, okay? And obviously, we can't give a computer a Lego set instruction and say, "Go for it," right? So to our point from before, right? You guys wrote in English because who was the operator of this? Who was going to be executing the instructions that you gave them? Some other dude in the class, right? Okay, well, and so you wrote in a language that was sort of appropriate for the recipient, the thing that was going to be implementing those instructions. Well, if the thing that's going to be implementing the instructions is a computer, we have to kind of do things in such a way that a computer can understand them, okay? And this is where things will get a little bit more complicated. But also, there's really sort of two layers here. Um, well, okay, let me demonstrate what I mean by that. Okay, so let me go to a an example from one of my other classes. Let's do, oh, I don't know. Let's just do, oops. Okay, so here's an example of a program that one of my other classes that we wrote for one of my other classes, my advanced CS or mid-level CS class. Okay, and this is just part of it, right? Because it keeps scrolling up. This is one of the pointers ones. Okay. You couldn't tell? Okay. Um, what is all this gobbledygook? Okay, it's a bunch of stuff in hex. Okay. Well, ultimately, right, when we program the computer, what ultimately does everything have to end up as? A bunch of ones and zeros. Okay, and here it's a bunch of ones and zeros. It's displayed here in hex because that makes it slightly more readable. Okay, but as you look at this, right, is this at all comprehensible to a human? No, of course not. All right, so let me scroll back down. Okay, whereas, is this comprehensible to a human? A little bit. Okay, this is written in C, um, and maybe some of it looks pretty. Some of it's kind of mostly readable. Some of it, maybe you don't know what all the decorations and stuff are supposed to mean. Okay. Well, let's do this one. Is this one readable? Less so. Although the guys in my class can read this and understand what each part is, right? So all of this stuff, right? Now what's going on here? What is this? Not clear what's going on because you don't know the language and you don't know what all these symbols are supposed to represent. Okay, now, when you're programming a computer, okay, there are a range of different levels at which you can program that. And what I mean is, how abstracted away from you are from the hardware are you? Okay, so in the very first thing I put on the screen here, which had just all that crap in hex, okay, that was like basically ones and zeros. That's about as low level as you can get without having to start thinking about individual transistors and the actual hardware itself, okay? Then at the very highest level, we could do something like, well, how many of you guys, when you were maybe a little younger in high school, did use Scratch or Make Code or the Lego robotics language? Any of those? Any that I'm leaving out? Okay, what was nice about those languages? They did, okay, but how did it simplify it? So like, let me take Scratch as an example. Okay, if you want to teach a child to program a computer, are you going to give them, um, are you going to show your kid this? Okay, well, maybe Mr. Runge will, but probably not, right? Whereas if I want to teach a child, so this is an example here, language called Scratch, and let me just start something just to kind of show you briefly what it looks like, and close the tutorial, okay? It's block oriented. So you put pieces of code together almost like you put together Legos, right? And this is certainly a lot more understandable for a child or a beginner, okay? Um, but this language, like there's a limitation of complexity that you sort of run into eventually with a graphical language, and you guys will learn that later on. Um, so what would be a language that, uh, well, has anybody programmed before in any language that's not block-based, like a textual-based language, other than Owen? Okay, yeah, what? Python. Anybody else for Python? Java? Any others? Okay, Python's probably the best example here because Python looks more human readable, okay? So what I mean here by we want the code to be both human readable and machine readable is, so let's take, for example, let me go back to the C example, okay? This is, you know, mostly human readable, okay? And it's machine readable in the sense that I have a program called a compiler that I give this source document and it spits out the actual executable, okay? So the process of converting from this mostly human readable, but still kind of technical looking stuff to something that actually runs, there's a program that's in the middle that sort of does all the details for me. And if I misplace any of the symbols here, it's not going to work. So for example, you'll notice that basically every line here ends in a semicolon. If I undo and remove one of those semicolons and then pipe it through this thing called the compiler, it's not going to work. The compiler will say, nope, there's not a semicolon where there should be one. I'm done. Fix it. Okay. Now, something like Python looks a little bit more friendly than this. Okay, so for example, let me just do, oh, well, there's a way though to do the, yeah. Oh, well, that's nice. Uh, I thought there was print. I thought there was a print line. Huh. Okay. Uh, all right. Is that a little bit more human readable than the C version? Right. If I'm just defining a number and telling it to print the number or whatever. Right. A little bit more human readable, and that actually is one of the advantages of Python, and why Python is, generally speaking, nowadays, if you're going to learn a programming language of any sort that's not graphical like Scratch or MakeCode or one of these sort of more kid-oriented languages, Python is probably going to be the one that you start with, okay, because it's the most human readable of them. Now, there is possibly one exception to this, and this may kind of show my age. How many of you have a TI graphing calculator? Okay. How many of you have it with you? No? Like actually in your bag or something? No? You do? Okay. Great. Which one do you have? Okay, an 84. Man, that's getting fancy. I had a TI 82 when I was a kid. And what's one of the things you can do with it? Oh yeah, you can make graphs. That's the whole point of a graphing calculator. Thank you. Try again. Thanks for playing. Did you ever program it? Play Snake. Yeah. Did you ever program it? Okay. What language did you program it in? Basic. It's called Basic. Okay. Um, and the Basic language, that was the first one I learned. Okay, back in probably what, elementary, middle school, somewhere in there. Um, so did anybody else program things for their TI, even if you were just typing in what somebody told you to type in for your TI calculator? Okay. When I was in algebra, what did we 100% program other than games? Doom. No. Believe me, our 82s could not run Doom. Uh, hell, the school computers could barely run Doom. Uh, yeah. How about a quadratic formula program? Yeah, we totally did that. Okay, and all kinds of other things. So we had lots of fun programming these things. Um, but that language Basic is kind of like the Python of the 80s in a sense, right? Uh, and it's, great for beginners. Okay, so let's see. All right, so let's take, let me actually open up one of my other examples from class. Oops, I want documents, examples. Um, let's do, say, functions. Oops. All right, let me just open up an example here. Okay. Um, okay, so let's just look at this thing and see, what are kind of the pieces that jump out at you. Like, we don't have to fully understand what this code does or why I wrote it or what the purpose is, but let's sort of look at what are the basic pieces, identify kind of what makes this language a language. All right, so what do you guys notice? What do you see? Okay, integer. Okay, so for example, in the bottom stuff there at line 18, int temp equals 1. Okay, what am I doing? What do you think that's doing? Okay, setting up that I have an integer whose name is temp, whose initial value or whose value is 1. Okay, now in terms of the stuff that we've done, right, how is this going to be encoded? Well, do we know how integers are encoded? Yes. Okay. And in this case, it would be encoded as a 32-bit signed integer. Okay, we, for simplicity, did everything with 8 bits, but the pattern for doing this with more bits is the same. You just have more bits. Okay, it's not any wildly different. Okay, so great. What else do you see? So let's look at, say, anywhere between lines 4 and 14. Okay, return. Okay, what else? Okay, if and else, right? So what makes computer programming is the ability to make decisions, okay? And have expressions that you might do one thing conditional upon something else, okay? Did any of you guys have the word if in your instructions for your paper airplanes? No, okay? There wasn't a need for a conditional set of expressions there, okay? But you could have, because you could have said something like, if your paper is oriented hamburger style, turn it an oriented hot dog style or something like that, right? Okay, and then, so we need conditional expressions. We have sort of declarative expressions like int temp equals 1. Okay, and then let's take one more example. What was something that we did when we talked about the Lego instructions? What was something that you occasionally would see in a Lego set instructions? The 2x or 3x or whatever, right? But some sort of need to repeat a procedure a whole bunch of times. Okay, so if I had given you the instruction that I want you to fold 1,000 paper airplanes, what would I have done? I would have handed you this set of instructions, and what would I have added at the bottom? Repeat 1,000 times. Okay, would I have written out this set of instructions 1,000 times? I could have, but would I? Of course not, because I'm lazy. Okay, all right, so what we're going to kind of do over the next few days is sort of look at each of these kind of things in detail. What do we mean by conditional expressions? What do we mean by iterative expressions, meaning things that repeat? We'll also talk about recursion, which is going to give you all a headache, so I'll warn you to bring ibuprofen that morning. And we'll play a game too when we do that. Oh yes, it's a really riveting game. Yeah, so that's kind of where we're going to go for the next week and a half or so. All right, I will see your smiling faces first thing Friday morning. Thanks for playing. Hope you have a good rest of your Wednesday. Oh, and before I forget, 2 interesting things are happening today, particularly freshmen. Anybody thinking about a CS major minor? No way? Oh, womp womp. So at noon, we're going to have the first CS club meeting of the semester in Goodrich. There'll be pizza, okay? And also tonight is the math and CS department's picnic. So if you're interested in math, CS, or just want to come have a free hamburger and hang out with a bunch of nerds, then you know where to come, okay? All right, see you guys later.